I would refer you to that. Okay, that's transport modeling, and that's the rage. Now, the next level of modeling is this chemical modeling. I don't know how many of you have gotten into chemical modeling yet, but chemical modeling is a really exciting application. In 1962, Bob Garrels and Mary Thompson published a paper on the distribution of ions in seawater, and they came up with the very first model which describes the behavior of ions in seawater and gave a mathematical description of that behavior. From that point forward, there was sort of an explosive development in all of these different models which describe speciation and reaction with the matrix through which the fluids are flowing. But see, many of these models just came and then fell by the wayside. Now, that's an interesting phenomenon. Why is that? There are really only about 5 or 6 models which have survived all of this time. The Salmonek, Watek, EQ36, there are a variety of models that have survived. And my question is, how many of them will survive over the long term? And I think the reason that we have lost so many is because there are hidden errors in these models. The users have found that the models do not fit the system and do not know how to interpret that difference between what they compute and what they observe. Now, the difference here is that in a chemical model, you do have a numerical algorithm in the center, this matrix inversion or iterative solution algorithm of some sort, but there's really no significant error in that part of the algorithm. It's not like a transport model where you have a numerical error of all sorts that you have to deal with. You have round-off error and you have ill-defined systems. In chemical modeling, you deal with the databases. You have a thermodynamic database, a chemical database, and you have a whole series of ancillary calculations that are done in the models. Now, see, this is an interesting point. When you use your transport model, you know all the constants that you put into that model. You know the porosity, you know the hydraulic conductivity. If you have a density term in yours, you know the velocity field. All that you know ahead of time. And so there's nothing hidden in that expression. It's just an algorithm. In chemical modeling, all of this is hidden to you except for the input chemical data. It's transparent to you. You don't even see it. It never even asks you if you like its equilibrium constants. It just doesn't. That's where the error is. And most of us are not aware of how much error is actually involved in that particular assumption. Now, how are these models used? They answer different kinds of questions. They answer, if you were to inject a fluid underground and it were to react in the subsurface, what would be the final resultant concentration of ions in that system? Or what would be the EH, or what would be the pH, or what would be the distribution of species? Or if I'm interested in transporting chromium, when we did our demonstration of chromium, is it chromium 3, is it chromium 6? What are the species involved in that? So there's mixing of waters and titrations and outgases and reaction path simulations, a whole variety of options that you can use chemical models for, all of them specifically decoupled from flow, coupled to flow only in a general sense. I want to give you some examples. If you look at, this is a problem that we continue to work on. This is the cross-section, a little different scale than we were talking about before, a cross-section through the panhandle of Texas. You see the scale here, this is 160 kilometers. So we're looking at the central part of New Mexico all the way to Oklahoma. Now the question here was, if we were to bury radioactive waste in this zone, build a nuclear repository there, what would be the subsurface conditions? If we had a breach in the repository and some of the contaminants were to react with the brines there, what would be their form? At that temperature, at that pressure, at that distribution of species, would we have migration? Would we have complexes, precipitation? What would be the subsurface environment? Now that's a difficult problem. Not specifically related to the flow field, which we know in a general sense, very slow moving, but before we have to transport it back to the biosphere, we need to know its current form. Okay? A chemical model allows you to build relationships like this. You can say, I know that there is a fundamental relationship between the amount of CO2 in my system, the partial pressure of the gases, the alkalinity values, which were represented by each one of these lines representing different values of alkalinity, the pH, and then this term that we call the saturation index. It's a quantitative measure of whether or not the fluid has the capability to react with the solid or to outgas. It's the ability to dissolve or to precipitate. Now, this kind of diagram is what is solved in a chemical model. It gives you the relationships between all of these different kinds of parameters. Now here's an example. We were interested in looking at 8,000 feet below the surface. We want to know what is the relationship between the gases that are present, the mineralogy, the species that are in solution. So we drill the wells and we pump the water to the surface and we measure in our surface laboratory the pH at the surface. And the pH that you measure at the surface is about 7.2. Obviously, we had some outgassing along the way. Now, the other thing that we can do, because we know this structure, this mathematical relationship between all the species, We can send a tool down, a wireline tool, collect a sample at 8,000, 7,000 feet, whatever zone we're interested in, at the ambient temperature there, at the ambient pressure, open up this chamber, which is a stainless steel, Teflon, steam cleaned, the whole thing, grab the sample, close it up, bring it to the surface, and then you exsolve the gases at the surface and very carefully measure all the components that are in that system. Now, we know how CO2 behaves. We also know how some of the other noble gases behave. They behave differently than CO2. But we also know then the chemical analyses of the sample. We know the temperature at depth. So we know the parameters necessary to redefine the subsurface conditions. So when you, using your chemical model, add back in the gases, elevate the proper temperatures and pressures, redistribute the species, you can calculate the subsurface pH. And when you do that, you get a value like 6.4, substantially different than the surface value. There's another independent approach that you can take, and you can make an assumption that things are equilibrium at depth. You can say, no, this is in a limestone aquifer. The water's been down there for 1,000,005 years, so there's no reason why it hasn't come to equilibrium. If I make that assumption, what would then be, based on some criteria for the solution chemistry on the surface, what would be the subsurface pH if I assume equilibrium with calcite, which is the predominant component in the limestone? And when you do that, you come up essentially with the same value, within 1/10 of a pH unit, the same value of 6.4. Now that's really exciting. But the problem is, we made an assumption here in this chemistry arena, which is the same assumption we make in transport modeling. In transport modeling, we often assume it's isotropic, it's homogeneous, the barriers are well defined. In chemistry, we assume equilibrium, 25 degrees, all kind of, the models, parameters are all correct. As a result, in both of those modeling arenas, we have error to deal with. Now, what we've decided to do is investigate in the chemical modeling arena how good our assumptions are. It'd be the same thing as doing your geostatistical modeling in transport. So we looked at anhydrite, because anhydrite's an important parameter. On the Gulf Coast, for example, they do a lot of injection into salt domes and into the cap rock. And anhydrite, of course, is a principal constituent there. And there's a reaction occurring there. So the question was, okay, in that kind of environment, we're injecting brines underground, what is the reaction mechanism, and how good would our assumptions be? So we decided, I'd like to do plutonium hydroxide, of course, but I think I'll start with anhydrite. So here's calcium sulfate, and you can write this reaction, calcium to sulfate. This is the thermodynamic equilibrium expression. The activities of calcium times the activity of sulfate gives you this thermodynamic value. Now, we also can say, if I measure the total calcium, I measure the total sulfate, then using a chemical equilibrium model, I calculate the activity. So I come up with an activity product. I can compare these two numbers together. Now, if this fluid is really in equilibrium with the rock, then the calculated value and the rigorous thermodynamic value should be the same. If they're the same value, then the ratio is 1, the log of 1 is 0, and I can plot this as what we call a log Q over K, or a saturation index. And if it's equilibrium, then the saturation index value should be 0. And most of you are familiar with that. I just thought I'd go through it very quickly. So here's another diagram that I published. Well, I'm really on the hot spot today. Here's one I'm not particularly proud of, but I do admit it. Here is a plot of saturation indices. Now, each one of these points, I think we need to focus that just a little bit if we could. If you look at each one of those points, each point represents a chemical analysis of a brine. The question is, are these waters actually in equilibrium with the mineralogy nearby? Now, the waters are very close to anhydrite. There's plenty of anhydrite in the region. It's also below an evaporite sequence, which has lots of halite in it. And many of the fluids will have moved along the halite phase boundary to get to that current location. Now, the question is, what is the error on that? Here, if you look at that cluster of points, they cluster close to saturation with anhydrite, but how much confidence can I put in them? Can I really say this water is in equilibrium with anhydrite, or this is super saturated? See, one of the other campaign that I'm on is that I think that we rely on this general concept of kinetics very often to describe our misunderstanding of the environment. I think that has become a wastebasket term. And one of the reasons is because we've improperly defined our error and uncertainty. So, we have a new model that we've developed called INTERP. This is a model to evaluate models. And we're interested in looking at a variety of models that are out there and whether or not those models are appropriately modeling what they claim to be describing. So you can choose the model that you want, generate your data set. I don't want to do that. And then you can generate some graphics. Now, probably some of the most sophisticated graphics that a lot of people ever deal with is this trilinear diagram. So we generate that, which is basically a mole fraction relationship between the species, between the different water compositions. So each one of these points would represent a chemical analysis in an aquifer. And as you know, you can relate the water composition there to a water composition there, and maybe you can, along a flow path, you can make some sense about some reaction mechanisms. I think we can go a lot further than that. I think the rage now in geochemical modeling is to do reaction path calculations, following a phase boundary, moving from point A to point B along a flow system, another kind of thing that we can do. But what I want to talk about today is this saturation index plot. We are interested in not only plotting the value, the actual calculation for that specific water, but how much error is associated with that. Now, there are two sources of error in this kind of calculation that are significant. One is the chemical analysis of the water itself, and we use this circle to represent that. We typically do a chemical analysis, and we have a cation-anion balance, which is our criteria for goodness. If it is within 2% or 3%, we think we have a good analysis. The only problem with that, and certainly in the environmental business, is that your sodium and your chloride could match within 2%, but your zinc and barium and lead could be off 2 orders of magnitude, and they never figure into that calculation. So you need to be, for whatever system that you're looking at, you need to know the level of error related to that species, using replicates or blanks or duplicates. What is the error? Whatever it is, you can use that error to calculate the degree of saturation error with respect to the minerals or the colloids or the amorphous materials that you're interested in examining. So that becomes the circle. The next level then is the little error bar that is added to the circle. And that represents the error in the thermodynamic data. That's the big problem. Okay, here is a plot. Originally came out, this is after a plot done by Harvey and Weir in 1980. And there they're comparing some models that are currently available. And I won't tell you the names of those models because they're pretty well known. But this is an evaluation they did of comparing some models to see how well they fit the actual solubility data for anhydrite. And you see these are actual solubility, experimental values for anhydrite in the white dots. And the green and the orange represent the model fits. Now there is and it's a very poor fit. If you see this one, it just moves right on off the chart. The solubility of anhydrite, anhydrite is not insoluble. One of the things that we've discovered is that as you increase the ionic strength up to very high values, the solubility increases dramatically as a function of ionic strength. So a new kind of a Pitzer expression called the ion interaction modeling, it's developed by Ken Pitzer at Berkeley, allows you not only to use the Pitzer expression, but to couple it with some semi-empirical expressions which give you a very tight fit to solubility data. Now that's important because we deal very often in brines and high concentrated solutions. Now I want to show you two equations. This is the expression that is typically used for concentrated solutions. If you have a solution that's more concentrated than, say, 1 molar, then you will move into the realm of an expression like this for de Pitzer. This is the typical de Pitzer expression, and this is the extension term. We typically call it the B dot expression. And you use this equation to calculate the activity coefficient, which is multiplied times the molality of whatever species you're interested in to get this activity value, which we need. This is the expression that is used in the models that did not fit well. Common expression. Now the newest expression is this one, this Pitzer expression. Now it's really not a very complicated expression because it can be broken down into pieces. All this expression here is essentially the Pitzer. You see the familiar terms there, ionic strength to the square root. And these parameters on the end are two kinds of parameters. They're related to the energy in the system, short-range forces, long-range forces, interactions between ions. And the parameters specific to those extensions are parameters that are obtained in simple experimental systems. And that's the real vertical breakthrough, I think, in this kind of application. Because you can get the parameters looking at simple sodium chloride, calcium chloride, salt experiments, binary and ternary salts. But the parameters are essentially additive in the sense that you can now take these simple salt parameters and use them in complex systems. So using a Pitzer equation, we now model the calcium sulfate solubility. And of course it matches very well. You suspected that. 25 degrees, look at this, almost to 7 molar sodium chloride solutions. You can model the solubility really beautifully. Then we decided, okay, that's 25 degrees. That's analogous to an isotropic homogeneous system. What happens if you raise the temperature? So then you go into this kind of environment. The real world, if I'm looking at the subsurface, how do these equations model the actual data? And it was a real surprise to us, but they do not fit. Now, what's the problem? Why is it that we have such very large error in our predictions? There are two more equations I want to show you. This is, I want to communicate this to you. It's a difficult concept. When you're using the Debye-Huckel extension, which we call the Pitzer expression, and calculating activities with that, you are calculating activities based on actual solubility measurements. You're actually looking at the solution of the compound of interest. When we extrapolate the equilibrium constant, which is what we're comparing to see whether or not we're at equilibrium, we typically use thermochemical values. So here you see the Vant-Hoff expression, which relates an equilibrium constant at 25 degrees to an equilibrium constant at some elevated temperature through this kind of relationship that Vant-Hoff derived related to the enthalpy of reaction at 25 degrees. Essentially, it's a linear extrapolation from 25 degrees, either up or down in temperature. Doesn't work very well when you go very far in temperature. You may also have an expression like this, which is a heat capacity power function expression, but very often we don't have really good heat capacity data. So very often we have parameters in here which are estimated or done by analogy. So the problem is that we end up then with a divergence between actual solubility data and extrapolated 25-degree values. So we end up we're comparing two things which we should not be comparing. So what we've done now is we've taken the actual solubility data as a function of temperature, and we've looked at that in terms of the Pitzer expressions as a function of temperature. And you see that we have a very nice relationship between experimental data and the Pitzer expressions. Once you develop that kind of polynomial, you then can predict the solubility of the minerals that you're interested in. In this case, we're interested in calcium sulfate in two forms. It's both gypsum and anhydrite. So we can distinguish the two as a function of temperature. You see we can go up even to say 200 degrees. Very tight standard deviation to our fits. Now with that kind of, armed with a weapon like that, we then go back to our saturation index diagram. Now the minerals we were considering before, of course, were anhydrite and halite, looking at these deep basin brines, whatever your brine environment would be. And we now have the ability to put an error bar on these points. We can look at the error between the chemical analysis, and these are new analyses, so we know the very precise error bar on those, and we also know the error in the thermodynamic data. And we can be much more confident in our ability to make predictions about whether or not we're actually at a phase boundary. And you see much of the fuzziness then disappears. Okay, where are we? There's two things that we've talked about. We've talked about transport modeling, the absolute crisis nature, in my opinion, of the state of the art if we do not consider error and uncertainty in that system. Chemical modeling, where we see the incredible attrition of models from the whole system because they have no mechanism for evaluating uncertainty and error, and only a few models which now will survive because there is an emphasis placed in looking at that error and their applicabilities to specific systems. So we have two kinds of modeling efforts that are moving along simultaneously. I should make a parenthetical statement that the rage now is to take the transport models and incorporate geochemical models into them. We call this coupled modeling. So we have now the error and uncertainty of the flow system and the velocity distribution there. We have the transport nature of it, the dispersion coefficients, and then we have the thermodynamic values, which are causing error and uncertainty in our system. So we're propagating error, and unless we deal with it now, we'll deal with it later. So, but the third kind of modeling, which I think is where many of us actually end up spending most of our time. I call this conceptual modeling because we can't be rigorous mathematically. Very often the chemistry is not available in the detail that we need, but we still have to solve the problem. We still have to know how far it's gone, where it came from, what is its likely flow path. I call this conceptual modeling. Here is an example. This is a coal-fired power plant in Germany. I use this one because it has lots of stacks. But it's a problem all across the U.S. We have utility plants all over the place, and we have enormous piles of fly ash and coal piles. And there is a solid waste disposal problem, but there also is a residual chemical problem as we see reaction with rainfall, snow, fluids from the slurries that react with these solid waste and enter the groundwater systems. Can we make any sense out of that? We see coal piles that have spoil piles like this, which are reactive, and off in the distance you can see the power plant, and if you were really good, you could see the ash piles in the back. Now, two of the constituents that are significant in this problem of solid waste and the residual chemical contamination of the aquifers are sulfate, and of course just general total dissolved solids, and boron. Now, boron is a contaminant problem because boron is toxic to plants. So anything above 1 milligram per liter, any plants are susceptible to that kind of thing. Now, most people are not really familiar with boron chemistry. It's kind of a unique element because typically boron forms what we call a Lewis acid. It's neutral. You think of an acid being charged. Boron is a neutral molecule up to about pH 9. That's its pK. Above that, it's predominantly an anion. So in this range where we deal with it most of the time in groundwaters, it's a neutral molecule. It also is not involved in redox. You don't ever reduce boron to any other species, and it doesn't form any slightly soluble minerals. It doesn't precipitate out as some boron salt. It does form some complexes in solution. You do form alkali metal complexes and some alkaline earth complexes, but they're very weak and are not significant. Now, if you look at fly ash, which is the principal source for these contaminants that we're discussing, fly ash, of course, is very small spherical particles. You have little spheres on top of larger spheres on top of very large spheres. Now, what happens is, in this burning process, many of the volatiles that are contaminants are volatilized, and then they recondense back on the fly ash particles. So you see chromium and some of the other species of metals that we're dealing with, and boron tend to concentrate on the surface phase, which means that they are rapidly soluble, highly mobile, and they get into the environment very quickly. So here you see other fly ash particles which have high surface area. Some of them are spheres on the inside, which increases their surface area. Now, we're interested in using boron as a conceptual model, as a tracer, and we're using as our tool the isotopes of boron. Now, there are two isotopes of boron, of course, B11 and B10. Now, these are stable isotopes. This is not radioactive. And this is the typical Dell expression that we use. Now, you use this for all your isotope expressions. You use this to describe the relationship between some sample that you're concerned with and a standard. And the standard that we use is an MBS standard, so everything is relative to that standard. Now, our first task was to look at the natural variation in the boron isotopes. And if you look at this, this is a plot of the del B11 for boron for naturally occurring minerals and fluids. And you see there is a wide range naturally of the isotopes of boron, all the way from seawater, which is around 40, to some non-marine evaporites, which are as light as minus 33 and minus 34. So you see there's over a 70 per mil shift naturally occurring in the fractionation for boron isotopes. And even beyond that, we see that over time there has been a progressive enrichment of boron. This is a plot of del B11 of boron as a function of time, looking at evaporites. And we see there has been an enrichment of boron even in modern seawater over time. So there is this changing mechanism as well as a broad fractionation of boron in the environment. Now, this is the mechanism we use to extract boron from water, to use our solid source mass spectrometry to do the analysis for boron isotopes. Now, one of the things that we've done is to look at the result of fly ash leachate and groundwaters contaminated by leachate. And we find that this coal burning process and the generation of ash generates a rapidly soluble, highly mobile boron, which is very much depleted in B11. We see in some instances that some of the ashes that have been leached are as light as minus 23 per mil, whereas most groundwaters that you look at very often are related to volcanic origin, are positive. So in environments where this applies, where you have a background value that is positive, you can have very strong fractionation in this isotope ratio for boron. Now, why is that important? Well, it gives you a tool, a naturally occurring tracer, which is the topic of this afternoon's poster session, and of course, not only naturally occurring tracers, but man-induced tracers, and also tomorrow's session. What are tools that we can use to evaluate the flow system? And one of the nice things about this kind of approach, and this is true about a variety of isotopes, is that for very small quantities of the contaminant, you can still detect its presence in the natural system. So for very small percentages of leachate, because of its large fractionation, because of the high concentration of boron, you can do mixing curves and you can calculate the presence of a contaminant and its source from the natural background value. Now, see, that's important in boron because, see, boron's always present in groundwater. If you do your chemical analysis for boron, it's always present. It can be 1/10 of a milligram per liter up to 1 milligram per liter. So as you look at the leading edge of a plume, it's indistinguishable from the background values. Where does this plume actually end? If I want to do my modeling of this system, how far can I go? So here would be a diagrammatic sketch. Here your disposal site. Now, we are interested in looking at the leading edge of this plume. If you look at sulfate, if you look at TDS, as you get a little bit away from the midpoint of that plume, it becomes almost indistinguishable very often from the natural composition of the groundwater. But using techniques like tracers, especially the naturally occurring tracers, so you don't have to get EPA approval or some approval to go put something in your system, you look at a naturally occurring tracer, a tool which allows you to define the leading edge of that dispersion curve. Now, you know, there are people in our university who don't believe anything about reactions along the flow path because they don't even believe we can model dispersion yet, which I think there's a strong argument that we can't. But when you look at natural systems and you can look at the distribution of species along these kinds of curves, it gives you a tool to define that point in our curve which we need for calibration. So another tool, conceptual modeling, which clearly indicates that this is not background boron. This is boron from a different source. So, in conclusion, let me just summarize this way. We are in a chemical data collection process. So much of the money that drives what we do is focusing around the chemical aspects of the data. And we need, we forget that. Maybe you don't, but many people do. The second thing is that there is a tendency, I think, to accept error. In fact, to ignore error. We all know it's there, but we don't talk about it. And I think we have lost an incredible amount of respect and credibility in this business of transport modeling and chemical modeling because we do not recognize that. Now, the first two we've talked about, and I think our universities are in big trouble because our students do not understand this process of evaluating both collection of error in the field and the collection of error, collection and evaluation of error from the laboratory analytical techniques. And then we give them a weapon. We give them software which has no error generating capabilities. So we have then a third level of uncertainty that we must deal with. And then finally, when we have to solve the real problem, we need to do this process, which I think is a real opportunity for us, this information transfer from the classical sciences, especially physics and chemistry, and even geology, where we use tools to solve fundamental problems. Let's take those tools and move them into the hydrologic environment and use them as interpretive tools to help us understand our very complex flow systems. And consequently, I think the importance of our session tomorrow and this afternoon is really emphasized. Thank you.
For more information on groundwater resources or to obtain additional copies of this videotape presentation, write National Water Well Association Order Department, 6375 Riverside Drive, Dublin, Ohio, 43017, or phone 614-761-1711.